You ever see a factory robot doing some delicate task, over and over, thousands of times, and it never messes up? Or maybe you've watched a CNC machine carve this super complex part out of a block of metal, and it comes out just perfect. Well, have you ever stopped to wonder how? The secret behind all of that incredible precision is a technology called the servo motor.
So let's dive right in. We're going to pull back the curtain on the engineering magic that lets machines control every little movement with mind-blowing accuracy. We're talking down to the sub-micrometer level, which is just wild. And really, this whole thing is a story of evolution, of how we went from simple, kind of dumb motors to these truly intelligent systems.
All right, so to really appreciate how brilliant a modern servo is, we got to go back in time a bit and look at the original problem. And that whole problem starts with the design of the old-school, traditional brushed DC motor. The workhorse of the early industrial age.
Now, these early motors, they had this one fundamental design flaw. They used these little physical brushes to make contact and get power to the spinning parts. And as you can probably guess, that created a whole bunch of problems. We're talking constant friction, which wastes power. The brushes themselves would wear down, creating dust and needing to be replaced all the time. Oh, and they would create sparks, which, is not only a fire hazard, but also creates a ton of electronic noise that can mess with other equipment. They worked, sure, but man, they were inefficient and a real pain to maintain.
But then, things started to change. By the 1960s, a little thing called solid-state electronics came along, and it made a totally new kind of motor possible. And look, this wasn't just a small improvement. It was a complete redesign that just got rid of the whole brush problem for good.
And here's the leap. Brushless motors completely threw out those physical wearing brushes. They replaced them with a smart electronic controller instead. And the result? Whoa. You get a motor that's way more efficient, has a much longer lifespan, is safer because there are no sparks, and needs pretty much zero maintenance. It was a huge step forward, a real game changer.
Okay, so the motor itself is way better now. It's more reliable, it's more efficient, fantastic. But this solved one problem and created a brand new challenge. See, having a great motor is one thing, but how do you tell it exactly where to go? And, more importantly, how do you know for sure that it actually got there? Well, the first and simplest way to do it is with what's called an open-loop system, but it's got a major flaw. The best way to think about it is like this. Imagine you're trying to throw a ball at a target, but you have to do it with your eyes closed. You can aim, you can throw, but you have absolutely no idea if you hit it or not.
And you can see why if you look at the process. Notice how the information only flows in one direction. The controller says, hey, move 90 degrees. The amplifier gives it the juice, and the motor moves. That's it. End of story. There's no signal coming back, no confirmation, no way to double-check if the job was actually done right.
This quote really just nails the whole issue, right? An open-loop system just hopes for the best. If the motor hits a snag or maybe slips a little bit, the system is totally clueless. And for any job that needs real precision, well, this just isn't going to cut it.
So clearly, that hope for the best strategy wasn't going to work for building robots or high-tech machines. Engineers needed to give the system, well, they needed to give it eyes, a way for it to see what it was doing and correct its own mistakes. They needed to find a way to close the loop.
And this is the real game changer. A closed-loop system is like trying to hit that same target, but this time you get to keep your eyes open. You're constantly watching your hand, you're comparing its position to where the target is, and you're making all these tiny little adjustments until you nail it perfectly.
What's happening here is we've created a continuous feedback loop. The controller sends a command, just like before. But now there's a sensor, it's usually called an encoder, attached right to the motor. And this encoder's only job is to constantly measure the motor's actual position and report it back to the controller. The controller then compares where it wants to be with where it actually is. If there's any difference at all, and they call that difference the error, it instantly adjusts the motor until that error becomes zero. And this whole system, this complete, self-correcting, closed-loop system, it has a name. It's called a servo mechanism. This is the core idea that makes pretty much all modern automation and robotics possible.
This is why it's so important to remember that a servo motor isn't just a type of motor. It's actually a complete system. It's a team. You've got the muscle, that's the motor that does all the work. You've got the eyes, that's the sensor providing all the feedback. And you've got the brain, that's the controller, the part that compares the command to the feedback and makes all the smart decisions.
So why do we care about all this? Well, this ability to precisely control motion and constantly self-correct, That is the absolute backbone of modern high-tech industry. Let's take a look at where these amazing systems are really putting in the work.
When you look at industrial robotics, servos are everything. They are what allow that giant robotic arm on an assembly line to swoop down, pick up a tiny little microchip, and place it perfectly on a circuit board. And then do that exact same motion, flawlessly, thousands of times in a row, without ever getting tired or making a mistake.
Or think about CNC machines, the ones that mill and carve and shape these incredibly intricate metal parts. Servos are what drive the cutting tools, and their insane accuracy is what lets those machines create complex parts for airplanes or medical devices with tolerances that are literally smaller than the width of a human hair.
And honestly, in automated factories, servo mechanisms are just everywhere. They're the key to the super fast, super accurate motion you need for everything from filling bottles on a beverage line to printing labels to weaving fabric. They give you that perfect blend of high speed and perfect precision.
So when you really boil it all down, the journey from a simple, old-school motor to a modern servo is really a story about adding intelligence to motion, right? We started with just a dumb muscle that was held back by friction and wear. We evolved it into a much more efficient muscle, and then finally, we gave it a brain and senses, creating a system that can fix its own mistakes and achieve a level of precision that basically powers our entire modern world.
And there you have it, the remarkable technology of servo motors, the hidden force behind all the precision we see around us every single day. And with this level of control basically mastered, it really makes you wonder, right? What's the next big frontier for automation? What challenges are we going to solve next?